Hi everyone, I am Bennila, working as an assistant professor in the Department of Information Technology from V.S.B Engineering College, Karur. In this video, we are going to discuss about the courses Theory of Computation, Unit 2, Regular Expression and Languages. This is the syllabus for Unit 2. Next, this is the textbook. There are two textbooks of Unit 2 objective is to construct models of regular expression and languages. This is the CO-PO mapping for Unit 2. Next, we see about the regular expression. Regular expressions are symbolic notation used to define search patterns in strings. So, some of the rules are used in regular expressions. One is epsilon. Is a regular expression which representing the language. Next one is the any symbol A from the input alphabet. Summation is a regular expression which representing the language. Next one is the union. Within bracket A plus B is a regular expression if A and B are a regular expression which represent the language A comma B. Next one is the concatenation. AB is a regular expression if A and B are regular expression. Next is the clean stop. A is a regular expression, 0 or more occurrence of A, forming a regular language. So next one is the regular grammar. A regular grammar is a formal grammar that generates regular languages. So, which consists of terminals, non-terminals, production rules, start, symbol. Terminals mean symbols that form string. For example, small letter A comma B. Non-terminal means variable used to derive string. For example, capital A S. Next one is the production rules. Rules for transforming non-terminals into terminals or other terminals. Start symbol, the non-terminal from which derivations begin. Types of regular grammar. Two types of regular grammar. One is right linear grammar. Another one is left linear grammar. So first is the right linear grammar. All production rules are of the form A belongs to small letter A, capital letter B, or A belongs to A. For example, S belongs to A, capital S, B, capital S, epsilon. Left linear grammar, all production rules are of the form A belongs to capital B, small a, or A belongs to A. Next one is the equivalence of finite automata and regular expression. The theorem is every language defined by a regular expression is also defined by a finite automata. Proof, let's assume L of R. For a regular expression R, we prove that L equal to L of M for some epsilon non-deterministic finite automata M with. So first, exactly one accepting state. Second one is no incoming edges at the initial state, no outgoing edges at the accepting state. So the first step is create a starting state, say that is Q1, and a final state that is Q2. Label the transition Q1 to Q2 as the given regular expression R. So from the figure 1, but if R is a Q, clean closures of another regular expression Q, then create a single initial state, which will also be the final state. Next, step 2. Step 2, repeat the following rules. State decomposition method by considering the least precedency regular expression operator. First, until no operator is left in the expression, precedence of operators in regular expression is defined as union, concatenation, clean, closure. So here in the union operator, that is plus, can be eliminated by introducing parallel edges between the two states. So this is the removal of union operator. Next is the concatenation operator or no operator at all. Can be eliminated by introducing a new state between the state as follows. This is the removal of concatenation operator. Next, clean closures can be eliminated by introducing self loops on states. So, which based on the following condition. So, the first one is if there is only one outgoing edge at the leftmost state, that is A in transition, A belongs to B, then introduce self loop on state A and label edge A to B as on epsilon transition. Second one is else if there is only one incoming edge at the rightmost state, that is B in transition, A belongs to B, then introduce self loop on state B and label edge A to B as on epsilon transition. Third is introduce a new state between two states having self loop labeled as the expression. The new state will have epsilon transition with the previous states as follows. So next is the proving languages to be not regular pumping lemma. So there are two pumping lemmas which are regular languages and context-free languages. So in the pumping lemma for regular languages states that for any regular language L, there exists on integer n such that any string. So x belongs to L with length modulus of x greater than or equal to n can be divided into x equal to UVW. So which is satisfying the following condition. Modulus of UV less than or equal to n, modulus of V greater than or equal to 1 for all I greater than or equal to 0, U, V, I, W, epsilon, L. The substring V can be repeated any number of times and the string will still belong to L. The pumping lemma is mainly used to prove that a language is not regular. If any pumped string does not belong to L, then L is not regular. So, which satisfying the pumping lemmas does not guarantee that a language is regular. So, next, closure properties of regular languages. A closure property is a characteristics of a class of languages such as regular context-free, where applying a specific operation that the operations are union, intersection, concatenation to languages within that class results in a language that is also within the same class. So closure refers to some operation on a language resulting in a new language that is of the same type as originally operated, that is regular. Regular languages are closed under the following operations. So L and M are regular languages. Clean closure, RS is a regular expression whose language is L, comma, M dot R star is a regular expression whose languages is L star. Positive closure, RS is a regular expression whose language is L, M dot R plus is a regular expression whose language is L plus L plus. Complement, the complement of a language L with respect to one alphabet E such that E star contains L is E star L since E star is a surely regular. The complement of a regular language is always regular. Reverse operator given language L, L or LR is a set of string whose reversal is in L. For example, L equal to 0, 0, 1, 1, 0, 0. L or LR equal to 0, 1, 0, 0, 0, 1. Next one is the union. Let L and M be the languages of regular expressions R and S respectively. Then R plus S is a regular expression whose language is L union M. Intersection. Let L and M be the languages of regular expression R and S respectively. Then it's a regular expression whose language is L intersection M. Set difference operator. If L and M are regular languages, L minus M equal to string in L but not M. Homomorphism. A homomorphism on an alphabet is a function that gives a string for each symbol in that alphabet. For example, H of 0 equal to AB, H of 1 equal to E. E extend to strings by H of A1 up to AN equal to H of A1 up to H of AN. Inverse homomorphism. Let H be the homomorphism and L, a language whose alphabet is the output language of H, H minus 1 of L equal to W. H of W is in L. Thank you.